So we're continuing on with part 2 of Piggies and Pools, lesson 2.01, our first lesson of unit 2. So we've already discussed a couple of concepts, discrete and continuous, as well as domain. And we've looked at a couple of different linear functions, one that's discrete and one that's continuous. Now we're going to look at a couple more examples. So I'm more sophisticated than my little sister, so I save my money in a bank account instead of a piggy bank. I get 3% interest on the money in the account at the end of each month. And if I take my money out before the end of the month, I don't earn any interest for the month. So we're getting interest payments in chunks. That tells us something about discrete or continuous. If something is chunked rather than continuous. I started the account with $50 that I got for my birthday. If I don't deposit anything more, how much money will I have in a year, which is also known as 12 months? What is our important information here? And it says to highlight the important details. I think this is a really great method for word problems, for story problems. We can go through and highlight the numbers or the things that are relevant to setting up the problem. So let's see, I get 3% interest. And I get it each month. Those seem relevant. I started with $50. That seems relevant. And we're looking for how much we'll have in 12 months. So that seems like all the relevant information there. And we looked a little bit at interest last unit. We're going to go over this a little bit again. So this should look similar to our prairie dog problem. We are earning 3% interest every month. So remember, with a percentage, we're going to move the decimal 2 places and then multiply. So in this case, we have 3%. That looks like this. The decimal point is right there. We're going to move it 2 places. Since we don't have a space there, we're just going to put a 0. And the decimal point is going to end up here. So it's going to be 0.03. And then we're going to multiply. So we have 50 times 0.03. Oops, not 0.3, but 0.03. And I put that in my calculator. I get 1.5. And remember, we're earning interest, so we need to add that to the starting amount. We get 50 plus 1.5, and that equals 51.5. That becomes our starting amount the following month, and we can do it again. But I'm going to show you a shortcut, so we don't need to go through all these steps every time. So here's our interest shortcut, or this is also known as percentage exponential growth. If something is increasing by a percent, like 3% per month, like this problem, our common ratio, we're going to have a common ratio, and it's going to be 1 plus the percent. So for example, in this case, we'd have 1 plus 0.03. So our common ratio in this example will be 1.03. And now we know, because it's a common ratio, we just have to multiply that every time. So let's use that shortcut to make it a little bit easier to fill in this table. So we know at each month we get paid interest, and we're going to use that common ratio. 1 plus the interest equals 1.03. That's going to be what we multiply by. So let me just get rid of all that because it might be confusing. We're going to multiply by 1.03, and if I put that in my calculator, I get 51.5. So 51.5 times 1.03 is 53.045. Now remember, this is money, and we don't have parts of pennies. So maybe we'll round here. We'll just round this to 0.5. So 53.05 times 1.03, I get 54.64. times 1.03, oops, 54.64 times 1.03, I get 56.28, and then 56.28 times 1.03, I get 57.97. So remember here we just multiplied by 1.03 each time. Our equation for this now, this one is multiplying, so we know this is geometric. So our form is going to be f of x equals a times b to the x. So a is our value at 0, that's 50 right there. And then b is our common ratio, which is 1.03, 1.03 to the x. We can graph this, graph these points. 1 will be 51.5, 2 will be 53.05, so just right about on that line. 54.64, be right about there. 56.28, maybe about here. And then 57.97 is probably right about on that line. Now this looks like a straight line, but we do know that it's geometric, so we expect this to be a curve. It just is a very, very slightly increasing curve. So if I were to try to draw a line over the top of this, we should see it deviating from the line, but it takes a little while. So you can see how those dots are starting to deviate from the line. They're just very slightly curving upward this way. And then they're going to keep curving upward that way, away from the line. So this is a geometric curve. It does not follow a line. We're going to ask the same questions we asked before, but we're going to ask them in a different way now. Is this function discrete or continuous? What do those words mean? So discrete meant that the line in between didn't make sense. Does this point in between make sense? Well, let's ask, in this problem we got a chunk of money at the end of 1 month. We got an interest payment, and we didn't get anything in the middle of the month. So this point in the middle of the month doesn't make any sense. This point doesn't make any sense. This point doesn't make any sense. None of the points in between make sense. The only points that make sense are the payments at the end of the month. So this is a discrete function. And then it asks, what is the domain? Do we remember what the domain means? The domain is our valid input values. So what are our valid x values here? Well, we said this middle one, this 0.5 isn't. 0 is, 1 is, 2 is, 3 is, but nothing in between. We have to ask, does it make sense to go backwards? Are we getting negative interest payments? Are they like going back in time and charging us? No, not at all. We started this bank account at time 0, so these don't make sense. These in-between numbers don't make sense. The only valid numbers here for our input are 0, 1, 2, 3, 4, which we can write just like that. 0, 1, 2, 3, 4, ... means it continues. Or if you remember these were called whole numbers, you can refer to them that way. But you don't need to. So this is an example of a geometric sequence that is discrete. Let's look at one more example. At the end of the summer, I decide to drain the 1,500-gallon swimming pool. I notice that it drains faster when there is more water in the pool. Interesting. So when I measured it, I found that 3% was draining out of the pool every minute. So it's decreasing by 3% each minute. Well, similar to how we have an interest shortcut, we have a draining shortcut, or, this could be like population dying off, anything that's decreasing by a percentage. We can use a similar common ratio shortcut, except now this time we're going to subtract instead of add. So we're draining the pool by 3%. So we're going to do 1 minus 0.03, and that's going to give us 0.97. That's going to be our common ratio for exponential decay. So let's take a look at how we use this in a table. Let's see, t minutes, so we'll just count these up, 1, 2, 3, 4, 5. And then we're going to multiply by 0.97 now as our common ratio. So 1500 times 0.97 is 1455, times 0.97 is 1411, times 0.97 is 1369, and I'm just rounding on these have decimal points. We're multiplying by 0.97 each time. Multiply by 0.97. I get 1328, and our last one is 1288. So you can see the pool is in fact draining. It's going down in the number of gallons that are left. We can write an equation. We know this is geometric, right? We're multiplying each time. So our format is going to be a times b to the x. A is our value at 0, right here. And then b is our common ratio, which we decided was 1 minus 0.03, which is 0.97. So overall, our equation is 1500 times 0.97 to the x. Now, once again, we can graph all of this. 1500 starts up here. We expect it to go down, so we made some room below it. 1455, so that's probably right about here. 1411, maybe around there. 1369 is maybe something right around here. 1328 is going to be right about there. And then 1288, our final one, will probably be about here. So you can see this is not quite a straight line. A straight line would come down here. This is kind of following a curve. If I could draw a curve, which I can't. Kind of following a curve that we would maybe expect to level off like that. So once again, our questions, is this function discrete or continuous? Is there a point here that makes sense? So at half a minute, had a certain amount drained. Well, yeah, because water is draining continuously here, right? So water is draining this whole time. So it makes sense to draw a line, and if you could draw an actual curve rather than a wiggly curve like I am. This would work the whole time. This function is continuous because the water is flowing. And then what is the domain of this function? Well, let's see. Does it make sense to extend it behind this? Well, the pool only held 1,500 gallons. It definitely didn't have more water in it before we started draining it. So no, that doesn't make sense in the context of this story. It would have been overflowing pool. So it looks like it starts at 0, but every value above 0 is valid. Not just the integers. The integers are valid as well, but so is 0.5, so is 1.5, So is 2.2619. All of these numbers in between are valid. So our domain is going to start at 0, and it's going to be everything above 0, including 0. X is greater than or equal to 0 is our domain. So that covers our objective for the day. Given a numeric relationship, I can correctly choose discrete or continuous in 2 out of 2 problems. We showed an example of a linear discrete, a linear continuous, an exponential discrete, and an exponential continuous.